Hello students, in yesterday's lesson we have discussed about HDFS architecture. So this HDFS architecture is a master-slave architecture which consists of components like name node and data nodes. Name node acts as a master and the data node acts as the slaves. So in this master-slave architecture, name node plays an important role in which this consists of metadata, means name node deals with the file system. It stores the metadata for all the documents and indexes in the file system. Data nodes are workhorses of a file system. They store and recover blocks when they are asked by the clients or the name node, and they report back to the name node occasionally with the list of blocks that they store externally. So in this fashion, this master-slave architecture works. So in this particular thing, we have also discussed about the secondary name node, which plays a supporting role in case of NAM node failure. So that also we have discussed in the yesterday's class. So with this understanding, let us proceed further. So in today's class, we will discuss about the Hadoop-specific file system types. So before beginning with this specific file system types, let us discuss few minutes about command line interface and some HDFS file systems. So what is this command line interface? So with respect to this, HDFS, so actually what happens in this particular case is that we actually view the HDFS, means Hadoop distributed file system, by interacting with it from the command line. So there are numerous different interfaces for HDFS. However, the command line is one of the easiest and most popular among the developers. So in this particular case, this command line acts as an interface between the user and the Hadoop distributed file system. So in this particular case, we use the command line interface. So already you people have, I think, referred the video postings of our college or our department, you can say. So in that particular thing, we have demonstrated how the command line interface is that, and also the installation procedure and some few commands. So that is what the command line interface. So this is the most easiest way to deal with or interact with HDFS file system. So let us continue. Some points we will discuss about Hadoop file system, that is Hadoop distributed file system. The Hadoop distributed file system, it is nothing but it's a file system which is accessed by user applications with the help of the HDFS client. It is a library that reveals the interface of the HDFS file system and hides almost all the complexities that appear during the implementation of HDFS. The user application is not required to know whether the metadata of the file system and its storage are on the same servers or have multiple replicas. So in our case, as an user, we have a command line interface is for our disposal, and also in this particular case, the HDFS files which plays an important role. So in this particular case, the user need not have to require to know where the metadata is, how the file, how exactly the HDFS stores the files and all. So this is for our what you can say the internal understanding purpose. So the user need not have to deal with that particular thing. So only he need to concentrate on his particular application. Continuing with this, the object of a file system class is created for accessing the HDFS. The file system class is an abstract base class for the generic file system. So how this file system is created? So let me show you some Java commands in this particular case. Means it is a kind of code snippet, you can say, Java code snippet for creating the file system object. File system object. Configuration object is config new configuration. File system FSys is the object, file system dot get config. So we are passing the constructor here. So here we create configuration object called config. With this command we create a file system object FS. So let us call this object as FS instead of FS. Make it simple. So the object of a file system class is created for accessing the HDFS files. The file system class is an abstract base class for a generic file system. The code created by the user for referring to HDFS must be written in order to use an object of the file system class. An instance of the file system class can be created by passing a new configuration object into a constructor. So this is the file system object called config as a constructor. It is passed here. Assume that Hadoop configuration files such as Hadoop default.xml and Hadoop site.xml are present in the class path. So this is about creating the file object. Next one is path setting. Path is another important Hadoop distributed file system object which specifies the names of the files or directories in a file system. We can create a path object from a string specifying the location of the file or directory on HDFS. Both file system and path objects allow us to perform programmatic operations on HDFS files and directories. So let us see how to create the path. So commands to create the path. So all these are the Java code snippets. So here in this first command, we create an object. We create an object for the path class. This first one, path fp is equal to new path file name. It creates an object for the path class fp. So in this particular case, we just check. This is for checking the file path. That is, if fs.exist fp, then the other code snippets. So in this particular case, this is to check whether the file path is correct or not. Okay. So the final output of our exiting operation in this particular case, it returns a Boolean value. If it exists, returns 0, otherwise 1. So this is how the path setting works. Next, similarly, after setting this, we can read from the file by setting this particular command fs data input stream object is fin fs dot open fp. So fs data input stream fin is equal to fs dot open dot fp, which is used to read the files. Then similarly, fs data output stream we can call it this object as fout fs dot create, which is used to create a new file or write onto that particular file. Fs data output stream fout is equal to fs dot create. So we must note that whenever a file is opened to perform the writing operation, the client opening this file grants an exclusive writing lease for it. Due to this, no other client can perform write operations on this file until the operation of this client gets completed. So we cannot, more than one client cannot have an access to the write operation of a single file. So that point should be noted. So in this particular case, so you need not have to worry about all these particular things. So these are been already, this particular thing is been demonstrated with respect to your first experiment and second experiment. Already it is been posted. So let's have an what I can say, look into those particular videos. So these are the initial setups, some few setups for HDFS file systems that already the video has been created by us and shared with you. So just go through that. So depending on the operating system and different installations that we use, so these the name of the commands may slightly vary. So that you should keep in mind. So let us, this is about the HDFS file setup and the command line. So now let us concentrate on Hadoop specific file system types. So in addition to ordinary files, Hadoop distributed file system also provides several specific file system types that provide richer functionality and simplify the processing of data. The local file system of the Hadoop performs the client-side checksum operation. When you write a record to a file, the client of the file system directly creates an hidden document called filename.crc. With the extension crc, .filename.crc. So for checksum calculations. So when you write a record to a file, the client of the file system directly creates the hidden document called .filename.crc in the same index containing checksum for each chunk of the document. So now in this particular case, the file system creates the checksum for the file that you are creating. So I hope all of you understand what is checksum. In your computer networks, I think you have used the checksum calculations, different cyclic redundancy checks algorithm. So based on that, this particular checksum is created for the file by the Hadoop file system itself. You need not have to worry about this. So in this case, if you don't know, just I will what you can say that tell you what exactly this checksum is. So this checksum refers to the number of bits in a transmission unit included with the unit to enable the receiver to see whether the same number of bits arrived or not. So this is the technical definition of the checksum. Means what? Whatever the data that is been that we are transferring, it has reached to the other side in the same format and same size. All the contents must be same. So this is called as a checksum, because in this particular big data we deal with the streaming of data. Okay, we are storing the data and we are analyzing the data in which is streamed data. So this is for this particular reason the checksum calculation is very much required, because whether the HDFS file system or a Hadoop architecture wants to know whether the file that is being shared to us, communicated to us, is it contains all the information that is being sent as it is from the client or not. So this is for this particular reason, this is the facility that Hadoop system provides, that is checking the checksum for each of the files. So you need not have to worry about this. All these particular things happens in background of HDFS. So after creating this file name .crc for the file for checksum calculations, then the size of the chunk is, this particular chunk is managed by one more file system, or what you can say, one more property, that is IO bytes, IO dot bytes dot per dot checksum. So this is one more Java feature that it provides this particular property to see all the checksum calculation, to manage the checksum for each of the file size. So the size of the chunk is managed by IO.bytes dot per dot checksum property, which is 512 bytes by default. So the chunk size is stocked up as metadata in the .crc document. So the file can be read correctly regardless of the changed setting for the chunk size. Checksums are checked when a record is analyzed, and if an error is found, the local system throws the checksum exception in this particular case. So before proceeding, let us see few more concepts with respect to HDFS files. So yesterday we have discussed some of these concepts like blocks, block placement. So in this particular case, I have told the pipeline and all replications of each of the files, means blocks in each of the in different racks and all. So the same thing here, the block placement. So the current strategy in HDFS is what? One replica on the local node and the second replica on the remote rack. The third replica on the same remote rack. So NAM node takes a decision about where these particular blocks is to be placed and how many of replicas are required. Why replicas are required for the file? Because in case if any one rack or a data node fails, we need not have to stop the processing here. Because in this particular case, streaming of data, huge data is very important. Okay, we need not have to lose that particular data, and also the time is very important. At what time the data is being collected. So for that particular reason, these data are stored as a chunks or a small blocks in a different data nodes of different racks. So that is what the replicas. So how many replicas and all those particular things, managing those particular blocks and all, it is been completely managed by data node, name node. You need not have to worry about this. That all things happens in the background. So one replica on the local node, second replica on the remote rack, third replica on the same remote rack. So yesterday in the one of the architecture I have shown with whatever is been, I have drawn that particular figure on the blackboard here. Okay, so the A, B, C. So there are different blocks or files stored in the same rack and also the different rack data nodes. Client reads from the nearest replica. Nearest replica means the nearest data node. Data node correctness is done using the checksums. As I have told, use checksums to validate the data. So these particular features are readily available with respect to the Java object classes. So file creation, already we know the client computes the checksum per 512 bytes. Data node stores that particular checksum, while file accessing, the client retrieves the data and checksum from the data node. If the validation fails, the client tries with another replica, means he looks into the another data node. So data pipelining we have discussed. So client retrieves a list of data nodes on which to place the replicas of the block. Client writes block to the first data node. The first data node forwards the data to the next data node in a pipeline. When all replicas are written, the client moves on to write the next block in a file. These are some of the properties that we have seen with respect to the HDFS yesterday. So rebalancing option we have also discussed yesterday. The goal is to reduce the percentage of disk occupied on data nodes should be similar. So usually means what? HDFS ensures that these replicas, all the replicas of the file should occupy the same space. If there is any variation, means what? There is we might think that our file system thinks that it is an corrupted data, or we have not received the correct data from as it is been sent from the from its origin. So and checksum fails in that particular case. So it ensures that the data node should be similar. Usually run when new data nodes are added. Cluster is online when rebalancer is active. Rebalancer is throttled to avoid the network congestion. So command line interface is preferred in this particular case. So with this understanding, let us discuss about the Hadoop-specific file systems. So these, whatever the checksum I am talking, these checksums are very economical to calculate with respect to Java. They executed in a local code, normally adding the marginal overhead to the time to analyze or write a particular record. So with this, let us start. Let us see what are the different Hadoop-specific file systems are. So in this Hadoop specific file system, we have different kinds of file systems exist. First one is the local file system. URI scheme means uniform resource indicator. It is called as a uniform resource indicator or identifier, you can say. Uniform resource identifier scheme. And then we have given the Java implementation for that particular local file system and what is the use of that. So first file system in HDFS is local file system. The URI scheme is, it is a file system only. Java implementation is fs.local file system. So just have a close look at the Java implementation code. It is an org.apache.hadoop configuration files. It is an local file implementation. FS means FS means a file system dot a local file system. So it's a file system for locally connected disk with client side checksums. A file system for locally connected disk with client side checksum. It is locally maintained. So as I have told, the replicas are stored. One copy is stored in a local disk also. So this is for this particular reason Hadoop requires the local file system. Second one is HDFS. So URI scheme is HDFS only. The Java implementation file system is HDFS dot distributed file system. So local system is not distributed, whereas HDFS is distributed. So it is an Hadoop's distributed file system. HDFS is designed to work efficiently with map reduce operation. So in this particular, you might have studied with the third unit. So map reduce is one of the technique which works on distributed file concepts. So that's why the HDFS file supports the distributed file system with map reduce operation. The third one is HFTP. Third one is HFTP. URI scheme is HFTP. The Java implementation code available in the property file called hdfs.hftp file system. So what is the need of this? So it is a file system which provides read-only access to Hadoop distributed file system. Often it is used with distance copy, used with dist-cp command to copy the data. Dist-cp. So distant copy. So actually this particular file system is oftenly used with to copy the data between two HDFS clusters running different versions. So to copy files between two HDFS clusters, this particular file system is used. It is read-only access. Then we have next one is HSFTP. This URI scheme is HSFTP and Java implementation is HDFS.HSFTP file system. So its use is a file system. This is a file system providing read-only access to HDFS over HTTPS. Okay, again HTTPS, because all these particular file systems are very useful for streaming data analysis. Next one is, so we have seen so far local file system, HDFS file system, HFTP file system, HSFTP file system. The next one is HAR file system. HAR file system. URI scheme HAR, Java implementation fs.har file system. So this particular file system is layered on another file system for archiving files. Hadoop archives are typically used for archiving files in HDFS to reduce the NAM nodes memory usage. So for getting the archiving facilities, so normally the Hadoop ecosystem makes use of this HAR file system concept. Next one is KFS, Cloud Store file system. KFS is the URI, fs.kfs.kosmos file system, Cosmos file system. So Cloud Store is distributed file system like HDFS or Google's GFS, which is written in C++. Actually it is written in C++ for cloud storage, for cloud storage facilities in which acts as a distributed file system like HDFS and Google. If that is the case, that particular kind of service is required, then we enable this particular file system. Next file system is, so in this particular case, so far we have discussed, we know that there are 5 In this particular slide, 5 different file system types are available in HDFS. Local, HDFS, HFTP, HSFTP, HAR, KFS, Cloud Store. So the next one is FTP. URI is FTP. Java implementation is fs.ftp.ftp file system. So this file system is backed by an FTP server. So this is the usage. Next one is S3 native. FTP is S3N. fs.s3native.native S3 file system. So this is a file system which is been backed by Amazon S3. So if you have come across the cloud storage facilities, so this Amazon S3 is one of the simple cloud storage facilities provided by Amazon. So if we want this particular storage service, then we need to use this Java implementation system, file system. Then the last one is S3 block based. If this URI is S3 and fs.s3.s3 file system is the Java implementation for this particular storage, file system storage. So this file system backed by Amazon S3, which stores files in blocks to overcome S3's 5 GB file size limit. So earlier one, we have the limitations here. There are different versions of Amazon S3 service. So with respect to that, if you want to deal with the block sizes, then dynamically, then we have to refer to this particular Java implementation file system. So these are some total 8 different kinds of file systems available with respect to HDFS. So these are different file types we can say that are available for our disposal. So depending on the nature of the analysis, nature of the storage of the big data, what we call, so we have to enable these kinds of services. So these particular things are very much helpful when we actually or practically in reality if we do some kind of analysis on the data. So I think after this, let us move to see some HDFS commands. So already we have shared our second practical video also. So that actually concentrate on the Hadoop file system commands. So we have shown the demonstration there. So in continuation with that, let us see which are all the different commands exist with respect to the HDFS. So various shell-like commands interact with HDFS directly as well as with other file systems supported by Hadoop, such as local file systems, HFTP, S3FS, etc. These commands are provided by the file system shell, FS shell we will say. This FS shell can be invoked by the command like say bin slash Hadoop FS arguments. So by invoking this particular command, we can invoke the F shell. So most commands in the FS shell are similar to the Unix commands you might have experienced with respect to our second experimental video. So let us see these particular things one by one. So amongst this, the first command is append to file. Okay, meanings are you can assume, you can predict what exactly the operation from the name of the command itself. So append to a file. So in this particular case, this particular command used for appending the single source or multiple sources from the local file system to file destination file system. This command also reads input from the standard input and appends to the destination file system. So if you want to append a content of one file to another file, then we can make use of this particular command. So we have shown the syntax also there. So HDFS, DFS, hyphen, append to a file. So for all the commands starts with a hyphen. So that you should note, hyphen, append to file. So the local source and to the destination. So in this particular case, after executing this particular command, it just returns 0 on success, or if it is error, if it has been the operation fails, in that particular case it throws 1. It returns 1. Similarly, the second command in this particular case is cat, which copies source path to std or standard output file, you can say. It is used for copying source paths to standard output file. This command returns 0 on success and -1 in case of error. Okay, so Hadoop FS minus cat or any URI, uniform resource indicators you can specify. Then the next command is checksum. It returns the checksum information of a file. Okay, so I want to know what is the checksum for that particular file in a Hadoop file system. So in that particular case, I have to make use of that. So just you need to specify Hadoop FS minus checksum and followed by the URI, means the file system. URI means the complete path of that file name, where what you are looking for. So that is what the URI meaning is. Hadoop FS minus checksum URI. So I have given some examples also here, and also it has been shown in the laboratory video also. Just practice those initial commands. So let us continue few more commands. So next one is change group, CHGRP. So we want to change the group. So in this particular case, change group association of files. The user must be the owner of the files or else the super user. Additional information in the permissions guide. The -R option will make the change recursively through a directory structure. So group association can be changed using this particular command. So Hadoop FS minus CHGRP. GRP means group. Okay. So -R is for recursively doing this particular operation in the directory structure. You can specify. The next command is chmod, change mode. So change the permission of files. So it is used for changing the permission of files, we can say. So the command syntax is Hadoop FS minus chmod minus R and the different modes what you want to change. Similarly, next one is change owner, that is CHOWN. So you can change the owner for a file. It is used for changing the owner of the files. The syntax looks something like this: Hadoop FS minus CHOWN with -R option if you are doing it recursively. Similarly, the next command is copy from local. Copy from local. Local is what? Local is nothing but the local file system. Okay, so earlier we have discussed Hadoop files, different file systems. So now in this particular case, copy from local. So now, for example, consider that I want to copy a file from a local hard disk or local file system to the HDFS file system. So in that particular case, it is to be used. So copy from local. So similar to put command. So what is put command, we'll see later. So except that the source is restricted to a local file reference. Okay. So copy from local. So Hadoop-FS minus copy from local URI means what? It copies the file from the local hard disk to the HDFS. Next, reverse operation of that, copy to local. Similar to get command except that the destination is restricted to a local file reference. Hadoop-FS minus copy to local. Copy from local, copy to local. So these are the some of the URIs you can mention. So both these options are available. Copy from local to the HDFS, copy to local, from HDFS to a local file system. So next command, so as I have told, the get command here. So just see here, get, which is used for copying files to the local file system. HDFS minus DFS minus get from the source. Okay, source to the destination. So source is nothing but it is an HDFS source and the destination is a local hard disk. So this is what the thing is. So just using all these three commands, we can copy the files from one location to another location or one file type to another file type, you can say. Next command under discussion in this particular case is count. Count the number of directories or files or the number of bytes of that particular file in this particular case, which is exclusively used for counting the number of directories, files and bytes under the path that match the mentioned file pattern. So the syntax in this particular case is Hadoop-FS minus count minus Q minus H and minus V. So after execution of this particular thing, it just returns 0 or minus 1 if it is a error in this particular case. So minus H option shows the sizes in human readable format and minus V option displays the header line of that particular file. So these are the different syntaxes you can practice in this particular case. So the next command under discussion in this particular case is make directory, mkdir, which is used to create the directories by taking the path URIs as an argument. So HDFS, DFS minus mkdir minus p. So these are so we can create a new directory into the specified path in this particular case. Then the next command under discussion is mv, which is used for moving the files from the source to the destination within the HDFS. Within the HDFS, we can move the files. So HDFS, DFS minus mv URI. So within the FDS, within the HDFS, we can move files from one location to another location using this particular command. Then remove, that is rm. It is used for removing or deleting files specified in the arguments. It is used for removing the files from the HDFS files. HDFS, FS minus RM, various options, minus F, minus R, minus R. So all these are minus skip trash. So using these particular things, options, this particular command, we can remove any file from the HDFS file system, not from the local system. It should be very clear. you should be very attentive in this particular case. You while using these particular commands, which commands are useful for what type of file, whether it is, are we dealing with local file system or are we dealing with the HDFS file system. We should be clearly aware of this thing. Otherwise, these particular commands may give error if it has been wrongly mentioned, wrongly give the references. So with continuing with this rm command, so just if you mention -rm or -rm, only files can be removed but directories can't be deleted by this particular command. And if you use -rm with an option r, then it recursively removes the directories and files also. Then one more in the syntax we have seen -skip trash. So it is used to bypass the trash, then it immediately deletes from the source itself. It will not go to the trash, it will completely removed from the source itself. Then one more switch command, that is -f, which mentions that if there is no file existing. Then one more switch command -r, which is used to recursively delete the directories mentioned. So these are certain commands which you can refer to. And also the same, this is with respect to your theory class is concerned. These are some of the commands. So the same commands we have executed and demonstrated in experiment 2 video. Just have a look of that particular thing and practice by yourself. So this, I hope this particular session which we have discussed about the HDFS file types and also HDFS few commands, initial commands. So let's practice these particular things and have a look at that particular lab video, experiment number 2. Then it will be clear to you. So I think it's time to wind up now. So I say goodbye now. Thank you very much.